go back to where we were. That's okay. So in the background, let this keep running. In the meantime, I've switched to the slides just to give some context, and then try to get back to where we were. So we were looking at lambda calculus, in particular type soundness, and what we're saying is that um, we were trying to prove this theorem of well-typed programs do not get stuck. And what we mentioned in the previous class was that we usually split this into progress and preservation. We looked at progress, right? Progress says that if lambda expression E has type T, then E isn't stuck. Where stuck means that E isn't a value and you cannot take a step. So this was progress. We proved it using Cork in the last class when we saw lambda calculus. Now we are going to do preservation, right? Preservation says that if an expression E has type T and you can take a step from E to E prime, then E prime has the same type T. So this seems obvious. So if you have an expression which is supposed to return an integer, if you take a single step of reduction, it magically shouldn't, the resultant expression shouldn't have the type, say, string, right? Um, this you need to prove, right? Because this is some fundamental property that sort of tells you that as you evaluate the expression, the types don't change. If they are supposed to return an integer, they will return an integer. So formally, this says that if E1 single step reduces to E2, and in an empty context, right, E1 has type T, then in an empty context, T2 has type T. In order to do this, we have to use several helper lemmas, right? So these are the lemmas that we are going to use. The lemmas themselves are going to be sort of generic, right? They are going to state some properties which are useful, useful irrespective of what you're trying to prove. The first lemma that we are going to use is called weakening. The idea is very simple, right? So this typing context, if you think about the typing context, it is sort of a map from free variables to values, right? And what this weakening lemma says is that if you sort of add more stuff to the typing context, right? Where additional stuff does not mean that you are changing any of the previous bindings. Let's say the typing context has x is an integer, and you add y is a string to the typing context. If some expression E had the type T in the original context, in the extended context, right, which is gamma prime, the expression will still have the type T because it is only referring to some original variables, and you added additional variables, so that shouldn't matter, right? This is the weakening lemma. This is useful because we will see that as we go through the preservation proof, we need to sort of expand. We will have an induction hypothesis that says something about a smaller context. We will end up with a bigger context with additional variables, and then we will sort of have to use this weakening lemma to make the proof go through. So you can think about sigma, the gamma prime, as a superset of gamma. So every mapping in gamma is also included in gamma prime. By mapping, they mean the key value pair, right? The same gamma, the same key value pair is also included in gamma prime. If it is included in gamma, there may be additional stuff, right? That's what weakening is saying. So let's do the weakening lemma first, right? So let's go step by step because what we're going to do now is we are going to first look at each of the lemmas. We are going to try to then do preservation and then use progress and preservation to prove type safety, right? Type safety says that if an expression has some type T, then it isn't stuck, right? So we will build up to that, but we are looking at the weakening lemma now. Formally, it is written as this, right? So we had this hash type relation. It says that under the typing context G, the expression E has type T, right? Then if there is a G prime such that for all xt, these are the pairs of the free variable and the type. If you look up x in G and it is some T, then it also means that G prime also has the same binding, right? It has a binding for the variable x, also the same value for the type as well. Then in G prime, right, E has type T. So by adding new variables, additional variables which are not referred to by this expression, we don't change the type. And we do this by induction on the typing derivation for this expression. We are going to induct on this inductor relation, which is hash type. Right? So as you'll see, there'll be some easy cases and then some few difficult cases. So the first one is the variable case, right? So it says, show me that the variable x has type T, assuming that you have this hypothesis, right? And given that if I look up x and G, I have some type T, right? So how are we going to assign the type? If you want to show that the variable x has type T in G prime, then we have a constructor, right? We have a constructor which just says that go and look up the type for this variable x in G prime. It should have that binding, right? That is the definition of assigning type to a variable. Let's just apply that constructor, right? We are just going to appeal to that. All it says is that if you want to show that, let me go back a single step. If you want to show that x has type T in G prime, then if you look up x in G prime, then it has to have some type T, right? What we have is, thanks to the way we frame the weakening argument, we know that variable x has type T in G, and whatever binding is there for G, it is also there for G prime, right? So we are going to directly appeal to this hypothesis that we have here. So if you apply to this hypothesis, we will get this as our new goal, and we can directly discharge that using this hypothesis here, right? That's what we're going to do. So we are going to apply H0, and we are now going to call assumption now. The second one is easy. The second one just says n, the natural number n, which is natural number n, has type nat. This is also a constructor, right? This is like a fact that we've added in our type checking rules. So constructor makes this go through. Now we have more complicated cases. So what we have now is, I want to show that E1 plus E2, the expression E1 plus E2 has the type natural number in G prime, right? But what I have is, I know E1 is a natural number in G and E2 is a natural number in G. And I also have the induction hypothesis, which says that for every binding in G, there is also corresponding binding in G prime, right? So we are going to use this as well. Let's just look at how this goes through, right? How do you type check the addition expression? Each of these individual expression has also need to be natural numbers, right? So by constructor, we get two sub goals where we are asked to prove these. And observe that the induction hypothesis, thankfully, is right in the right shape, right? So we have hash type. So I'm going to apply I hash type 1 for this sub goal, and that gives me this this goal, and this is precisely our assumption. This is the assumption that we made. Every binding is also there in binding for G prime. That's just there. So assumption makes it go through, and similarly for the other case. So that's fine. Yeah. Now what is this? This says that abstraction has type T1 or T2. Again, in order to show that abstraction has the type, we have to appeal to constructor. It says that if you extend G prime with this additional binding for the free variable, which is type T1, E1 should have type T2. Again, this is also very straightforward. Use the induction hypothesis that goes through, right? What we end up having is we get this term. Let's simplify it first. And okay, so let's look at what is there, right? So now that we've simplified it, you have to sort of stare at the rules. It says that I want to show that if I extend G prime with this binding x for T1, and if I look up x0 in that, it has to be some T. This is what I need to show. What I have as part of my assumption is that if I start with G and I extend that with xt1, which is the same as here, and I look up x0, then it has the type T, right? this is the assumption about the gamma, and we are going to show something about gamma prime. There is one extra binding here, right? But the observation here is we don't know anything about this x and this x0, right? This x is some variable here. Sorry, x0 is some variable here, x is some variable here. So how do we actually say anything about the relationship between x and x0? Because if you look at the induction hypothesis, right, it says something about looking up x0 in G prime. But we are actually looking up x0 in a G prime extended with x to t1. And the trick that we apply here is that we are going to analyze two cases where x is equal to x0 or x is not equal to x0. Those are the only two possibilities, right? If x is equal to x0, then if I look up x0, then I will get t1. That's the first one. And if x is not equal to x0, then if I just look it up, it must be the same as looking up x0 in G or x0 in G prime, because we know that x is not equal to x0. This is just a map, right? We are just looking up key values, keys in this map from outside in. So that's the reasoning that we are going to use. We are going to use cases for each one. I'm not going to expand this because it is sort of obvious once you do this analysis, but you can see what I can show this. So we are going to do case analysis and then simplify in E auto. So yeah, so it goes through very simply with that. So yeah, but the important aspect is trying to do this x equals x0. And thankfully, our functional maps are built in a way that it knows what happens. Just to show you how this appears, right? If I do cases x equals x0, then this breaks up into two different cases, one for x equals x0, right? And if I do simplify, I have some t1 equals t, some t1 equals t that goes through, right? That is just assumption. And this one is into simplification, right? And I have this here which matches the assumption here, right? So you apply h0, we will get this goal, and that goes through, right? Thanks to this assumption here. So apply h0 and assumption. So that's the idea there. And the last one is also very simple. This is similar to what we had done for the addition expressions. So they have the exact same structure. In order to show application goals, you have to show that this is a function type. This is a type whose where the type matches the argument type of this function. And those two just go through thanks to the induction hypothesis over on this side. So that's weakening for you. So we've done weakening. So that's one down. We have a few more to go. Substitution is an interesting one. Okay. Substitution again says, assume that you have a typing environment gamma, and you have this one variable, interesting variable x, whose type is t prime, right? And we've extended gamma with this binding here, right? This whole thing is the gamma. Now, under this typing environment, if E has the type t, right? And you have a separate expression E prime, which under empty context, it doesn't use any free variables. Under an empty context, it has type t prime, right? Observe that this t prime is the same as this t prime, right? Then, if you take the original gamma, right, this gamma here, and you substitute E prime for x in E, then the type is preserved, right? So what is the intuitive meaning here? E may refer to x as a free variable, right? So E may refer to x as a free variable whose type is t prime. All I'm saying is that wherever x appears, if I replace x with the same typed expression, a more complicated expression, but it has the same type, and by definition, it doesn't refer to any free variables, right? So if I replace x, the variable x, with the same type expression E prime, then the type is preserved. So a simple example would be that you have x plus 1, right? Assuming that x has type natural number, x plus 1 also has type natural number. I can replace for x the expression 5 plus 5, because 5 plus 5 also has the type natural number. So by replacing x with 5 plus 5, I will preserve the semantics, right? This is what substitution is saying, right? This is obvious, but this is quite useful when we actually try to do the small step reduction. So this is what we are going to prove next. So here is the substitution as encoded in Cork. So we are going to do the same thing, right? So assume that there is a G, right? And we have an additional binding which is x to t prime, and expression E has type T, and we have this expression E prime under an empty context has type T prime. So this T prime is the same as the T prime here. Then if you take the original gamma G here, you substitute E prime for x in E. So wherever x appears, substitute E prime, then the type will be preserved. So essentially this says that substitution with the similarly typed expression preserves typing, right? So this is required because as we take a step, where is this required? As we take a step in preservation, right? We will be doing substitutions, and we want to show that substitution preserves typing, right? That is why we want this particular lemma. Again, the way we are going to prove this is we are going to induct on the typing derivation here, right? This derivation here. We simplify. Here it appears we have a if statement which says x0 equals x. As we have seen previously with these complex expressions, right? We want to do case analysis where we've seen matches or ifs. We just want to do case analysis. So we do case analysis here where I just pick the expression x0 equals to x. So you get a true and false cases, right? So first thing you get x equals x0, in which case we can sort of continue. So if you simplify, we get some t prime equals t. So we can invert this to know that t equals t prime. And once you do that, what we end up with is an interesting one, right? So we end up with a hypothesis which says that under an empty context, E prime has type t. So this is coming from this one, right? But I want to now show that under some G, E prime has type t, right? So because E prime does not have any free variables, even without free variables, we can assign the type, right? So we know that the type is t. By extending this empty context with some other context, it might be any context at all. We now want to sort of say this has type t as well. So this is precisely where weakening is useful, because this is what we proved earlier with weakening. So when you apply weakening, you will say that, okay, I need to find a assignment for this unification variable, right, which is the smaller set. And for the smaller set, we will just unify that with an empty set, right? And then we want to show that if I find any binding for empty set that is also in G, this larger set, empty set does not have any bindings. So that trivially holds, right? If you simplify, you get none equals some t0. So because empty set does not have any binding, we just get none. So we can derive contradiction in the assumptions. So that goes through. So that was when x was equal to x0. When x is not equal to x0, we have the other case. We can simplify this. So observe that I want to show that this variable x0 has the type t. So I'm going to appeal to the constructor, which just says that look up x0 in G, you should find t, right? And that is the assumption that we have already. So that one goes through as well. This is very simple again. So this is just I just need to show that the natural number n has type nat. So just the constructor makes it go through. Here, this is the addition expression, right? But we are doing substitution in both sides. So E1, E2 are the expressions. I'm substituting E prime for x in both of the expression, because that is how substitution works. So let's apply constructor, which breaks that proof obligation for each of the sub expressions. Both of them still have to be natural numbers, right? Um, and uh, and again, just like earlier, we have the induction hypothesis that makes these things go through. So that goes through easily. And as we looked at earlier, we have a if here. So let's do case analysis. First thing is we have x equals x0, and we want to show that um, if you look up this expression, right? Sorry, the type of this expression in G is T1 arrow T2. So let's do constructor, because now we can break it up into the obligation for just the body. Right? If you invert E, what we learn is that x equals x0, so that gets substituted. And once you do that, we can now apply the weakening rule. So let's apply the weakening rule. So we have this particular larger set now. We are going to apply this to a smaller set. So let's find out how that works out, right? So we have a smaller set that will show up. So let's apply weakening. So we have, this is a smaller set that we are going to find, right? So we are going to find an assignment for this gamma with E1 and T2. We have that here, right? So this gamma gets unified with this term. So one thing to observe in this term is that we have two types for x, right? So this is xt. Sorry, I have trouble with my phone. I'll just okay. Now it should be fine. So observe that something interesting is happening here. We have the type t prime for x as well as type t1 for x. So the way to look at this is we search for things from outside in, right? So if it matches, if I look up x, I will get t1 out of it. So that's the assumption there. Keep that in the back of the mind, right? So the proof obligation is has type some unification variable e1 t2. We have an obligation, we have a assumption which pattern matches with that, so that goes through. Now what I have to do is that because I've pattern matched that here, that has filled in here. If I look up x0 in this term, if it returns some t, then for this new one, right? If I look up x0, then I get the same t, right? Here the point is that I'll just simplify for this. Just like earlier, right? We don't know anything about x0 and x. x0 is a variable, x is another variable. So what are the possibilities here? It is either the case that x0 equal to x, or x0 is not equal to x, in which case we are going to look up in G. Similarly here, right? x0 is equal to x, in which case we'll get t1. Here also we'll get t1. We won't get t prime, right? That's the observation. If x0 is not equal to x, we'll just look up x0 in G. And for that, we have a induction hypothesis, which will make it go through. So we'll do case analysis first, and then this simplifies, right? So if you simplify, all you have is we have the same type for both, so that goes through. If x0 is not equal to G, observe that we know that x0 is not equal to x, so both of these won't match, right? Because we know for a fact that x0 is not equal to x, so we are going to look up directly in G here, right? So if you simplify, this just looks up directly in G, and we have the same idea here, right? So just to step back and step forward, we know that x0 is not equal to x. I'm looking up x0 in this one, and I know x0 is not equal to x, so this is going to be simplified into looking up in G. Right? And the observation is that even in the assumption, the same thing is going to happen. These two terms are going to match. Right? That is what makes this proof go through there. The rest of the proof is sort of very straightforward. It's maybe I'll just do one step. So here is I'm going to show the type of this abstraction. So apply E constructor so that we extend the type with the typing environment with the type for the free variable, and I have to show this type. I will apply the induction hypothesis which matches the term, right? So this induction hypothesis matches this term. Okay, so that's done. And the interesting thing that comes up here is that observe that I have G here. I have x0 t1. I have x0 t1, x t prime, x t prime. This is some t prime, right? This is unification variable. But observe that these two bindings are in the different order, right? So I have x and x0. I have x0 and x here. So doing trivial, right, will not make it go through, because you cannot really show that these two terms are the same, because they are not, right? They are the same because if you look up these terms, of course you need to unify this first, right? That is also there. But if you look up any variable in this map or this map, you will get the same result, right? This is not simple equality. This is equality based on the semantics of the map. And hence we use this tactic called maps equal. I think this is the first time we are using this tactic, but it is doing equality based on the semantics of how these F maps work. Two maps are said to be equal when, if you look up a particular key, they return the same value for both the maps. That's the idea that we are using here. So maps equal makes it go through. Right, so that's done. Final one is straightforward. I'm not going to cover that. So we've also done substitution now, right? So we've proved substitution. Okay, so slowly we are building up. The next step is we want to show preservation for the step 0 function. So we are in a state, we are in this, our small step semantics include the step 0 function and the step function that includes evaluation context. We will first show that this holds for the step 0 function. This is preservation theorem applied for the step 0, which says that if E step 0 to E prime, if E has type T, E prime has type T. Observe that the main preservation theorem says something about the step function, right? Not the step 0 function. Okay, so let's do that. So preservation 0, we call it preservation 0. If E1 step 0 to E2, E1 has type T in an empty context. E2 also has the same type. It just preserves the type, right? So we will make the proof go through by inducting on the derivation of the step 0. So we don't induct, we invert that. So we learn each of the cases. We are doing case analysis here, right? So that's what is happening. Sorry, I said induction. So we invert on one, we simplify. So we get the different cases. What are the different ways in which we can get the type for this? There is only one way, right? So this is application. So this needs to have an abstraction type. This needs to have a type that matches the abstraction. So let's invert it. Yes, so we get the abstraction type here, right? The function type there. And this value has to match the type, this one. So that's there as well. Let's invert H4. So what will we learn? We learned that, I mean, if this type is an abstraction type, we can do, if we extend the type of empty type with the X for T1, E has type T. Why is this the case? This is because of the type for abstraction, right? That is the definition of how we type check the abstraction. So in order to type check abstraction, what we do is we extend the context here, which is an empty context here. We extend that with the type T1 for X. And in that extended context, E has type T, right? That is what we learn from inverting this term, right? E has type T, right? And now, if you, I mean, look at these two, right? Look at this one and look at this one, right? Under some empty context, under assumption of the variable X has type T1, E has type T, and I'm substituting, right, for the x, the value v in expression E, where the value of, where the type of this value v is also T1, right? These three precisely match the substitution lemma that we just proved. So we are just substituting for this free variable x. E may refer to this free variable x, and wherever this free variable may occur, I'm just going to substitute that with this value v, whose type is the same, right, T1. And I want to show that the type is preserved. This is precisely what we proved in substitution. So we directly appeal to the substitution lemma, right, which now asks me to unify this with this term here that goes through. And I need to also show that V has type T1 that is also going through directly. And this one is very simple. This just says that assuming that N1 plus N2 has type T, then N1 plus N2, the mathematical expression, right, on natural numbers also has the same type T. This is, I mean, the definition is straightforward. So you do inversion of that, you learn these things, and by constructor, they just match the assumptions here. So constructor makes it go through. So we proved preservation 0. We need to take this to preservation, right? The thing that is sitting in between is we have to reason about evaluation contexts. And for that, we have another lemma, right? This lemma also is intuitively very simple, right? If you sort of say, says if any type E1, actually, oh, okay. So if E1 has any type, right, and E2 has the same type, right? So, and if you plug E1 in this evaluation context, there is some type for that whole expression, right? The expression E1 itself may have some type, but if you plug it in a larger evaluation context, the new expression may have a different type, right? But if you take E1 and replace that with another expression which has the same type, that is what E2 is. So if E1 has some type and E2 has the same type, then in this evaluation context C of E1, if you replace E1 with E2, then the type will be preserved, right? This is also obvious. So if I pick a term which has some type, say string, and I look at focus on the expression E1, which say has the type natural number, if I replace that E1 with any expression that has type natural number, then the evaluation context, the whole expression, has the type string, right? So this is also obvious because we are replacing an expression with another expression which has the same type, right? So this is what we call generalized plug here. This particular lemma is what we call generalized plug. Yeah, I'm actually going to skip this. This is sort of very straightforward. This follows the same argument as what we have used earlier. So there is nothing new here. So I'm going to skip it. So once we've done that, we can now write down the preservation theorem and prove it. So if E1 steps to E2, E1 has type T in an empty context. E2 also has the type T. We are going to invert, just like how we did for step 0, we are going to invert this step relation, right? We get a bunch of dependent assumptions, right? How plugging should be done. That's there. The thing that we do here is we actually apply a correct expression that we are replacing in this generalized plug. I'm not going to focus on the details here. You can have a look at what happens here. All I'm doing is I'm going to apply generalized plug, right? I'm going to apply generalized plug here, where I'm going to give a particular assignment for E1 prime, right? And that assignment is going to be E1, right? All I'm saying is that I have an expression E1. I'm going to pick E1 prime in that for all. I'm going to assign that to E1, right? I'll leave the details for you to focus on. Again, nothing much is going on there, but except that I'm just going to assign one particular argument. If you've if you've done OCaml, right, and you've sort of looked at or what other language has this? So this is equivalent to doing labeled arguments, right? So if you say in OCaml we have a thing called labeled arguments, where you have like if you have 3 or 4 arguments and you want to specifically partially apply say one argument, you can just name that argument and apply it, right? So that is precisely what is happening here. I'm going to apply generalized plug where the argument e1 prime, which is one of the for all variables, I'm just going to specialize that to e1. And once you do that, you get a bunch of sub goals, right? All of which match the assumptions, right? So plug these two plugs goes through. When you simplify, you also get this as type. Okay, so maybe this is interesting. So what do we have here? I want to show that E3 has the type T0, right? And I know that E0 has the type T0, and you can step 0 from E0 to E3, right? You can step 0 from E0 to E3. I know that E0 has type T0. I want to show that E3 has type T0. Now, this particular thing is what we proved in preservation 0 earlier, right? And I directly appeal to that. That asks me to show that there is a step function. This matches with this, right? And then show that E1 has the type T0, which is what this one is. And then the last one is, sorry, this one is, oops, this one is, goes through with this. Let's step through it, right? So first, step 0, there is some unification variable here, goes to E3. This is unified with E0, right? And then I want to show that E0 has type T0. That's the assumption. And finally, E1 has the type T. That also goes through. So, okay, so we've done preservation now. What we now need to do is to actually go back, right? We need to show that the safety, the type soundness theorem holds. We are going to use progress and preservation. But the important thing is we are going to sort of build upon what we've done earlier in all of the course. We have built up this infrastructure for proving stuff with invariance, right? We are going to appeal to that now and make this proof go through. One of the cool parts about this presentation, right? The way of doing type safety in how Frapp does. If you sort of go back and read papers that prove type safety, soundness using types, right? Let's just leave it at that. They sort of present that as a separate mechanism, right? They sort of say, okay, this is a distinct mechanism from various ways of reasoning about programs. Proving soundness of programs using type safety is sort of presented as a distinct mechanism with its own development and so on. But here, what we are going to do is to show that this way of proving soundness of programs is just an instance of how we've done transition systems, how we developed invariance and so on, right? You may not appreciate this because we've not seen the usual way of presenting type safety, but keep that in the back of the mind, right? So, yeah. So here is the safety theorem, right? What does the safety theorem say? If an expression has type T, then not stuck is an invariant, right? So if the expression E has type T, then for the transition system that is formed by E, unstuck is an invariant. Unstuck is an invariant for the transition system. So again, even the framing of this theorem is hinting at how we developed all of this infrastructure earlier. Typically, we don't present it this way. We just say that this expression has type T and this expression is unstuck. We will have to sort of build everything from scratch there. Here, by just proving progress and preservation separately, we are actually going to use the infrastructure that we've developed for reasoning about transition systems. We are going to apply that. Right, this is actually quite cool. So first thing we do is we just do simplify so that we push all of these left-hand side of implication to the hypothesis. The first, so how have we shown that a particular invariant I holds for a transition system, we've used invariant weakening, right? So we've used invariant induction as well. But what we've done is we've used invariant weakening, and we've shown that the stronger invariant actually is also an invariant for the system, and the stronger invariant implies the weaker invariant. The weaker invariant here is that it is unstuck, right? It is either a value or it can take a step. The stronger invariant that we pick is precisely the typing relation, which is that this particular expression E has type T. That is the stronger invariant that we pick. And we are going to say that if the stronger invariant holds, if E prime has type T, then E is unstuck, right? That is what we are going to show. But it directly sort of is an application of the progress and preservation, as we will see, right? So we are going to show this invariant. We cannot show this directly, so we are going to sort of show a stronger invariant, and we are going to show that the stronger invariant implies this. And the stronger invariant that we pick is that E prime has the type T, right? That is what we are going to pick. Okay, so now the invariant now becomes the stronger invariant that we have to show, right? So we are going to show this by invariant induction. So this is what we've done previously as well. So we are going to apply invariant induction and simplify, right? And yeah, so firstly we have a we have E equals X or false. Actually, that's not the E equals S, right? So if you substitute E for if you substitute S for E, then you will have hash type $0 ET, which is what the same as this one. So equality makes it go through. Now observe what we have, right? We have I can step from S to S prime, and S has type T, S prime also has type T. This is what I need to show. This is precisely preservation, right? This is exactly what we showed with preservation. So if S has type T and you can take a step from S to S prime, then S prime also has type T. And we directly appeal to preservation theorem here. So we apply that. We want to show that S prime has some type, right? And S prime has type, we can step from some expression to S prime. That expression is going to be S, right? And S has type T, S has type T, that's part of that. So that's there. So that's done, right? And now we again simplify. So this is the, so if you sort of stare at this, right? This is the, we proved that stronger invariant actually is an invariant for the transition system. Now we need to show that the stronger invariant, which is that expression has the type T, implies the weaker invariant, right? So this is exactly progress, right? That's the observation. That's the beauty here. So this is what we proved in progress theorem. So if an expression has some type T, then it is unstuck, right? So if you simplify and apply progress, that proof also goes through. That is directly going through. So what have we achieved at the high level, right? We've shown that if you have in this particular simply type lambda calculus, if you have an expression which has the type T, if you can actually type check an expression, then the expression will not get stuck, right? We've done that using progress and preservation. And we've sort of built upon the infrastructure that we've seen for the transition systems, the operational semantics, right? This invariant weakening, invariant induction is from transition systems. We are sort of appealing to that directly. And we are using progress and preservation to show type safety course. So in your assignment, which I haven't released, I should release it today. What you will do is you will prove the type safety of a more complicated system. So you will have lambda calculus. You will have types, but you will also have subtyping. So we've seen some variants of subtyping. This will be a particular variant of subtyping. I'll leave the details for you to figure out, right? So, but what you will have to show is that that system also has type safety. So the lambda calculus with subtyping, if you can assign a type, then the expression will not get stuck. Right? So that is what you'll have to do in the next assignment. It'll be quite fun. There'll be actually most of the steps, right, will be very similar to how we've approached each of the progress and preservation steps. That is the reason why I went through in detail. There will be one or two places where you need to be a little bit clever. I won't spoil the fun for you. It's actually not too difficult if you can sort of see what those steps are. But otherwise, the proof and the system will be sort of very straightforward. And there is some, you will not have seen this sort of subtyping earlier. There'll be a description in the question. Part of the challenge in this assignment is for you to figure out, it will be formally described, for you to understand the formal system and then to work out what will happen. So there'll be, I think, there'll be both width subtyping and depth subtyping. Again, I'm not describing anything more. All of that will be described in the assignment question. Read it. It'll be very familiar. What you've seen so far, you will know how to what it means. I want you to learn it and then go ahead and prove it. The proof itself is going to follow the same strategy, right? All you need to do is to read the material, understand it, and then apply similar techniques. There'll be one step where something interesting will happen, but otherwise the proof is very straightforward. I will stop here. Actually, I'll stop here, and then we can catch up tomorrow. I think we have a public holiday on Wednesday, if I'm not mistaken. Is that right?
Yes, sir.
Okay. So let's start compiler correctness tomorrow. Yeah, it's a fun little topic as well. We are going to again build upon operational semantics. If you want to sort of do some interesting reading for that, there is a compiler called ComSet. So ComSet is a C compiler, right? So the interesting bit about ComSet is that it is a formally verified C compiler. What does that mean? Unlike GCC or LLVM, it has semantics. It has formal semantics. In particular, if you have some semantics for the source program, right, source C program, ComSet compiler will ensure that your compiled assembly in x86 will also have the equivalent semantics, right? This is so awesome, right? Because C compilers are used everywhere, from all sort of devices to warplanes and whatnot. And when you use GCC or LLVM, you have no guarantees, right? Some optimization completely changes the semantics of the code. ComSet ensures that according to its own definition of what the semantics of the source C program is, the target program also preserves the semantics. This is the whole ComSet infrastructure is written using Coq, right? And interestingly, this was written by the same person, Xavier Leva, who also invented OCaml, right? So ComSet is an interesting project. ComSet uses this proof technique called assimilation in order to prove the correctness of the compilation phases. We are going to study simulation in order to prove compiler correctness for a very simple language. We are not going to do C, full C. It's just C is just a large language. We have our own favorite language, very simple language with our command language and assignments and so on. We are going to study compiler correctness. How do you frame the argument for compiler correctness from the next class? And it will sort of give you some insights into what do we mean by formally verified compilers. Right? So that's the intention. We'll catch up tomorrow. Yeah, Vishnu.
So I actually had a request. So I mean, even though like solving assignments is fun, sir. I mean, I felt like having assignments every week isn't that great. Like we have been having assignments every week except for the midsem break. Like they're having a off break with no assignments or something.
Oh, you want to break with no assignments?
Yeah, I mean, I'm not sure if others feel, but that's what I felt. I just wanted to
That's
make that.
fine. That's fine. What I'll do is I'll just give, maybe you can take 2 weeks for this assignment, right? That way, if someone wants to start, they can start early, right? I would have given a week. Is that okay, Vishnu?
Yes, sir. Yeah.
Okay, so I'll release the assignment. I understand how this course is going to be assignment after assignment. Yeah, so let's do 2 weeks. I don't mind. Um, is it okay for others? Yeah, okay. I would be surprised if someone says no, we want more assignment. Um, yeah, okay. So let's do that. Feel free to bring these things up, right? It's a very small class. I want you to sort of enjoy this. If it's getting a little too much, let me know. Then we can dial down the assignments and such, right? Um, so yeah, so I I think assignments are the only way to learn the material in depth, but it doesn't have to be every week, right? So if we skip on one assignment, that's fine. So let's do 2 weeks for this assignment. So today is Monday, so we'll do Monday after the next one as a deadline for this. Okay, good. So I'll stop here. I'll talk to you. I'll talk to you tomorrow. Okay, no worries. Talk to you later. Bye bye.